Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired, and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. Level 17 determined by direct integration. The moment of inertia of the shaded area with respect to part A, the x-axis, and B, the y-axis. So here is the given figure. So for this problem, let's have a horizontal strip as our guide strip in answering this problem. So the length of the strip is x and the thickness is dy, as shown, and the distance of the strip from the x-axis is y. So therefore, differential Ix is equal to distance square y square times differential area, which is x dy, where x is from y equals x cubed, so x is cube root of y. So differential Ix is y square, quantity cube root of y, or y to the 1/3 dy. Ix therefore is integral of y to the 7/3 dy. And integral of, by the way, the variable of integration is y, so the limits will be from 0 to 8. The integral of y to the 7/3 is y to the 10/3 over 10/3, so Ix is 3/10, quantity y to the 10/3 from 0 to 8. So Ix is 3/10 of 8 to the 10/3 minus 0 to the 10/3, which is just 0. So using the calculator, Ix is 307.2 inches to the fourth. For part B, Iy is, we have a rectangular strip, moment of inertia with respect to the y-axis. The base is 1/3 of x cubed dy. Then x cubed is just y, so differential Iy is 1/3 of y dy. So Iy therefore is 1/3 integral of y dy from 0 to 8, and integral of y dy is y square over 2 from 0 to 8. So Iy is 1/6, quantity 8 square minus 0 square, and Iy can now be computed. It is equal to 32 over 3 inches to the fourth. Level 18. Using integration, compute the polar moment of inertia about point O for the circular sector. So for our solution, let's have a circular strip arc as shown. So that every element of this differential arc or arc strip will be equidistant from O, and the distance is denoted by small r as shown, and the thickness is differential r. So that JO or IO or IZ is equal to JO differential IO differential IZ is equal to distance square r square times differential area. Now the differential area is the area of this strip, circular strip, which is just the length of the strip times thickness differential r. The length of the strip from plane geometry is equal to the radius of the arc times central angle in radians, and the central angle is 2 alpha. So therefore, differential IO, which is differential JO, differential IZ is distance square r square times differential area. Again, the differential area is arc length, radius times 2 alpha times thickness differential r. So differential IO equals differential JO equals r square r times 2 alpha differential r. So that IO or JO is integral of 2 alpha integral of r cubed differential r. So IO equals JO equals 2 alpha quantity r to the fourth over 4 from 0 to r. So obviously it is alpha big R square over 2. So IO equals JO equals alpha over 2 r capital R to the fourth minus 0 to the fourth. So it is alpha R to the fourth over 2. So that's it. Level 19. Calculate the moment of inertia of the shaded area about part A, x-axis, and B, y-axis. So no doubt, we have to consider horizontal strip from the figure. Although we already have a guide formula for moment of inertia with respect to the x-axis and y-axis for this configuration. It's just big area minus this area here. So I don't want you to memorize formulas. What is important is the concept, so that you don't need to memorize formulas. So the length of the strip is x and the thickness is dy as shown, and the distance of the strip from the x-axis is y, so that differential ix is distance square y squared times differential area, which is x dy. So differential ix equals y squared, then x dy. So ix, x, by the way, is from this equation is square root of 3y. So differential ix is y squared times quantity square root of 3y, then dy. Ix therefore is square root of 3 integral of y to the 5 halves dy. 2 plus 1 half is 5 halves. So ix is square root of 3 y to the 7 halves over 7 halves, and reciprocal of 7 halves is 2 over 7. Since it is y that is the variable of integration here, limits of y would be from 1 to 4 inches. So using the calculator, ix is 2 square root of 3 over 7 times 4 to the 7 halves minus 1 to the 7 halves, which is just 1. So ix is equal to 254 square root of 3 over 7, and that is approximately 62.85 inches to the fourth. So differential iy is 1/3 x cubed dy by the formula for moment of inertia of a rectangle with respect to the base. So this is the base, the y-axis, and x cubed is from this equation 3y equals x squared, so that this becomes x cubed. We raise both sides of the equation to 3 halves, so 3y to the 3 halves equals quantity x squared to the 3 halves, and 3 to the 3 halves is 3 square root of 3 times y to the 3 halves equals x cubed. So therefore this is the value of x cubed. Substitute here. Differential iy is 1/3 of quantity 3 square root of 3y to the 3 halves dy. So cancel out 3. Iy therefore is square root of 3 integral of y to the 3 halves dy from 1 to 4. Integral of y to the 3 halves is y to the 3 halves dy is y to the 5 halves over 5 halves. Reciprocal of 5 halves is 2/5, so iy is 2/5 square root of 3, then y to the 5 halves from 1 to 4. So iy is equal to 2 square root of 3 over 5, quantity 4 to the 5 halves minus 1 to the 5 halves. And using the calculator, iy is equal to 62 square root of 3 over 5, or approximately 21.48 inches to the fourth. So remember that you can use your calculator actually from here, because the calculator is allowed. Just check that it is equal to this value. Same is true here. You can use your calculator, and same is true with this. So my purpose is to let you master and recall integration by just power formula. These are just power formulas. And I mentioned earlier that we have a guide from level 4 problems. There were two for this region, because it is just big region minus this uh, empty region. And I want you to remember that, or to recall the formula and substitute here. But because this is uncommon area for practical reasons, I just want you to familiar with the moment of inertia with respect to the base of a rectangle, because that's a mass, triangle, and circular sections. Those are the important sections in structural engineering. But if you want to extend to parabolic sections, then you can do so. But it is basic requirements that you should know the moment of inertia of common and practical sections such as rectangular, triangular, and sections involving circular areas.